Hello, welcome to Basics of Finite Element Analysis Part 2. This is the 7th week of this course and today is the 3rd day. What we will do today is solve a problem on heat transfer, and so essentially we will be solving the Poisson's equation in context of heat transfer, and as we solve this problem we will also learn a trick or a technique whereby we can reduce the size of the domain for symmetric problems by factors of 2, 4 or even 8 or even larger. So, first let us look at the problem. So, this is the problem for heat transfer, and here we are assuming that A11 is equal to A22 is equal to 1 and A12 is equal to A21 is equal to A00 is equal to 0. So, in that case my governing differential equation becomes minus grad square u equals F naught, and we also assume that F naught is equal to constant. So, just to make our problem simple, even though we do not lose any complexity in this thing. So, or this can be also written as minus del 2u over del x square plus second derivative with respect to y, and this equals F naught. So, this is the governing differential equation, and this governing differential equation is valid at what locations? It is valid for the domain of the problem. So, whatever is the domain. So, in this case we say that the domain of the problem is a rectangle. So, we can say that it is like a plate. So, it is a square plate, and for purposes of simplicity, so here this is my x axis, this is my y axis, and for purposes of simplicity the size of this plate is 2 by 2. So, the coordinates are 1 comma 1, 1 comma minus 1, minus 1 1, or minus 1 minus 1, and it is minus 1 1. So, the size of the plate is 2 by 2. So, here U represents temperature and F represents heat generated per unit area. So, this differential equation this is valid at all the points, at any point in the domain. It is not valid on the edge, on the boundary. Also, we have to know the boundary conditions of the problem, otherwise we cannot solve the problem. So, we say that the boundary condition is such that on all 4 sides u is equal to 0 on this side, u is equal to 0 on this side, u is equal to 0 on this side, u is equal to 0 on this side. So, what have I done? I have basically on all 4 sides, let us say I have put it on in ice, but the okay. So, on all the 4 edges I have ice, and that is what I am doing. So, our aim is to find T, or not temperature, T u at all points in the plate. So, the boundary condition which I said is gamma. So, note that here I have not put a superscript E, because this is the domain of the entire plate. This is the boundary of the entire plate. When I am talking about at element level, then I will put a superscript E. Okay. So, this boundary condition is valid for the entire plate or for all the boundary, and this equation is valid for all points in the system. Now, one way to solve this is I can break this up. What do we do? First step is we discretize the domain into a lot of small elements, then we develop a weak form, then we put interpolation function in it, we develop element level finite element level equations, FE equations, assemble them, apply the boundary conditions and solve it. So, in that case, I mean we will get a solution, no problem. But we also, classes of problems, we can also exploit the fact if it is symmetric. So, what we see here is that in this case, so this is a symmetric problem. What does it mean? What it means is that when we will get the solution of it, just by looking at this problem, we can say that the solution at location xy will be same. So, what does symmetry mean? That if I have any point, let us say x1, y1, then the solution at x1 minus y1 will be same. If that is the case, then there is symmetry across the x axis. If the solution is also same at minus x1 y1, then there is symmetry across the y axis. So, in this case, just by looking at the problem, I can say that this is a symmetric problem, it is a symmetric problem, and it is going to be symmetric across the x axis and also across the y axis. Why do I say that? So I can say that here symmetry exists along x and y. So, this problem is symmetric. Let us just consider the x axis, we can use the same argument for y axis also. I will explain why is this symmetric along the x axis. It is symmetric along x axis because of a combination of 4 reasons. See, the problem will have a solution, and its solution will depend on what? It will depend on a geometry, right? The solution is going to depend on geometry. It will also depend on material properties, right? It will depend on material properties. Third thing, what else it is going to depend on? It will depend on boundary conditions, right? And the fourth thing it will depend on, it depends on 4 things. The fourth thing, look at the equation, x relates to geometry, right? X and y, they relate to geometry. There is BC, and then also we have said that A11, A22, they are related to material properties. So, we have considered geometry, we have considered material properties, we have considered boundary conditions. There is one more thing in the equation which we have not considered. What is it? Huh? F naught, right? U is the solution. So, that is something we have to predict, but F naught. So, if the force term, and in this case the force term is heat generated per unit area. So, it will depend on 4 parameters. It will depend on geometry, it will depend on material property, it will depend on boundary conditions, and it will depend on force term. Now, if I think that the problem is symmetric along x axis, then the geometry has to be symmetric along x axis, right. So, I have positioned my coordinate system in such a way that it is indeed symmetric. It is a square plate, it is symmetric in the along the x axis, right, in this case. So, I fulfill this condition. Second thing is, the material properties have to be symmetric along x axis. What that means is that if there is any point x1 y1, then at another point on the other side of the x axis at the same distance, the properties should be same. In this case, the material properties are A11 A22 is equal to 1, which means these properties are same in the whole field. So, properties are symmetric. Properties are symmetric. Third condition, boundary conditions should be symmetric. What do I see? U is 0 on the top edge and U is 0 on the bottom edge. So, boundary conditions are also symmetric. And the fourth condition is force term. Force term is F naught, and the value of F naught is same. It is not a function of x and y, it is a constant. So, again it is same at all the places. So, that is also symmetric. Only if all these four conditions are satisfied, we can exploit the feature of symmetry. If even one of these is not exploited, then we cannot say that the problem is symmetric in nature. So, this is very important to understand. All these things have to be simultaneously true, then I can exploit the feature of symmetry. So, what we see here is that the problem is symmetric not only along the x axis, but it is also symmetric along y axis. So, in that case, what I will do is I can only discretize 1/4 of the domain and solve for only 1/4 of the domain. I do not have to solve for the whole domain. What that means is that if I require 4n elements for the entire domain, right, then if I am only solving for 1/4 of the problem, I need only n elements. So, my computation will be faster because number of equations will go down by a factor of 4. Okay. So, a lot of times you may see in your problems presence of symmetry. If it is symmetric along one plane, you can divide your problems, complexity goes down by half. If it is symmetric along two planes, it goes down by factor of 4. It can be symmetric about 3 planes, or it could be axisymmetric also. So, we will exploit this feature of symmetry. So, then my reduced problem is this. Okay. So, reduced problem is this. So, please note, we have not shifted the coordinate system, because once we have put the coordinate system at the center, the location of the coordinate system also tells us whether it is symmetric or not. So, now we are taking the first quarter of the problem and the coordinate system has not shifted, okay, and this is the reduced problem. Now, what is the boundary condition on the top edge? U is equal to 0. On the right edge, U is equal to 0. Now, the other thing we have to note is we have to know the boundary condition on these two edges. The boundary condition on these two edges. Here in the original problem, we knew boundary condition on all 4 edges. Unless we know the boundary condition on these 2 edges, we cannot solve the problem. So, what will be the boundary condition on this edge? What is the boundary condition on this edge? I will give you an answer. You have to first understand the physics of the problem. Suppose there is this point x1 y1, and on the other side it is minus x1 y1. The value of u at x1 y1 and minus x1 y1 will be same because of symmetry. Okay. So, when you take these 2 points which are very close to each other, let us say this is P1 and this is P2, the value of point P1 and P2 across the line of symmetry will be same, right, which means that the value of u at point P1 will be same as u at point P2, right. It is the same thing, we have said it so many times, right, because of symmetry, which means what? And if these 2 points are extremely close to each other, if they are extremely close to each other, so let us say the midpoint is this P3 which is at the center, then what is the value of del u over del x at point P3? What will be the value? 0, right, it will be 0. So what symmetry tells us is, a direct mathematical consequence of the symmetry tells us is that on this edge the derivative del u over del x, this is my primary variable, the derivative of primary variable along the plane of symmetry in the direction normal to the plane of symmetry will be 0. It does not mean that del u over del y will be 0, right, on this line. So this is the, so it will be only del u over del x will be 0. What about here on this line? Del u over del y will be 0, but del u over del x will not be 0. The tangential component will not be 0. The normal component to the boundary will be 0. Okay. So in general, I can say that along plane of symmetry, del u over del n, where n is equal to 0, where n corresponds to direction normal to plane of symmetry. So with that understanding we will do, so these are the extra boundary conditions. I will enforce del u over del x and del u over del y 0 on these planes. So with that understanding, what I do is I break this up, and let us say I break it up into 4 elements for purposes of this class, and my global node numbers are 1, 2, 3, 4, 5, 6, 7, 8, 9. And my local node numbers are 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, and my element numbers are element 1, element 2, element 3, element 4. Agreed? So if I do the math, Kij for each element, if I calculate it in local coordinate system, you have seen it earlier, then it will be so what is the size of each element? Overall size was 2 by 2. Now the size of the overall domain is 1 by 1. So each element is half by half. So if I am doing this in local coordinate system, so I will integrate it between 0 to 0.5, 0 to 0.5. Agreed? Okay. So, this is dx bar dy bar, and because I am using local coordinate systems, I say x bar and y bar. And what are psi I and psi j? So, for each element how many psi's will be there? For each element how many approximation functions will have? 4 approximation functions, because it's a 4 noded linear rectangle. So, psi 1 is equal to 1 minus 2x. We have derived these relations earlier, so I will not go back. Psi 2 is equal to 2x bar into 1 minus 2y. Psi 3 equals 4x bar y bar, and psi 4 equals 1 minus 2x bar 2y bar. So, using these we can develop expressions for each K matrix and also for the F vector dx dy. So, eventually I will get a K matrix times U. So, this is for each element. Right. And finally, so this will be how many equations for each element? So, it will be 4 equations per element, 4 equations for each element, and my after assembly I will get a overall global K matrix times a U vector equals a global F vector plus a global Q vector. Okay. And how many equations will these be? 9 equations. Why? Because in the global domain we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 9 nodes, right. So, we have 4 equations per element. So, at element level we will get 16 equations, and those 16 equations will be reduced to 9, right, because of elimination of 7 degrees of freedom. What are those 7 degrees of freedom? They are associated with node 2, node 4, node 5, node 6 and node 8. Okay. So, what we will do is, so I get 9 equations and then I apply boundary conditions, right. I apply boundary conditions, but before I apply boundary conditions, and what are the boundary conditions? First, related to the primary variables, right. So, the boundary conditions are that U3 is equal to 0, U6 is equal to 0, U9 is equal to 0, U8 is equal to U7 is equal to 0. So, how many terms are 0? 1, 2, 3, 4, 5, 5, right. So, if I apply boundary conditions on primary variables, then these 9 equations reduce to how many? 4 equations, because U3 is equal to U6 is equal to U9 is equal to 3, 6, 9, 7, 8, U7 is equal to U8 is equal to 0. Okay. So, eventually I am left with a reduced number of equations, and the size of those number of equations is 4, right, because these 5 things got eliminated. And what are the things which are left? U1, U2, U4 and U5, agreed. And here we have global K11, K12, K14, K15, and similarly we can fill up this matrix. The last row will be K51, K52, K54 and K55. So these are reduced number of equations. And here I get F1, F2, F4, F5 plus I get some Q terms, right. So this will be Q, and I will not write the global thing, but I will write it. So the first, this will be because of, so I am going to erase this because it is generating some confusion. So this will be Q11 plus X, right, F1 will be Q11, Q11. Then Q2 will be Q21 plus Q12. Third thing is Q3 is 0. What else is Q4? So it is 1 4 plus 3 1. Right, 1 4 plus 3 3 1, and the last one is the fifth, and this will have 4 contributions. So it will have, I will not write this, but there will be 4 terms. Now this Q12 plus Q21, first look at this term Q11. Now we know that Q's, so these are basically related to Qn. If you go back to our earlier thing, and we had written it as del u over del x nx plus del u over del y ny. This thing had to be integrated, right, and the term here was basically integral over the domain w q n d omega ds, right. This is how we used to get at element level, right. Now so Qn, in this case for Q1, what is ny? Ny is 0, ny is the direction cosine of the normal to corresponding to this edge 1 3, right. So this is 0, and also del u over del x at the first node, this is 0 because of boundary condition related to symmetry, right. Same thing here, this Qn is equal to 0 at node 2 due to symmetry. See this thing, this I can also write it as del u over del n, okay, and we know that on a plane of symmetry, see this is, and along any plane of symmetry del u over del n is 0, and this is nothing, this entire expression is nothing but del u over del n. So when I multiply this del u over del n with w and ds and integrate it, because the integrand Qn is 0, its integral will also be 0. So this is also 0 because of boundary condition, symmetry, because of symmetry. What about node 4? Node 4 is this, node 4 is this. Again on this at node 4, del u over del n is 0. So, it is not that the sum is 0, individual components, this is 0 and this is 0, same thing here, individual components are 0. It is not that the sum is 0, individual components themselves are 0 because of symmetry. And finally, we look at the fourth term, and fourth term relates to this mid node. Okay. Fourth term relates to this mid node. What is this value? So, these first three terms in the Q vector, they were 0 because of the boundary condition related to symmetry. What about this sum? We had said that if a node is shared on all four sides, if it is shared, then the flux which is going in is same as flux which is coming out. So, when I add up all the individual, if it is shared from on all the sides, then because of that condition this is all 0, right. Okay. So, it just happens in this case that the entire Q vector is 0, but that may not be case in all situations. In other situations you will have to look at it. So, with that understanding, I get a K matrix times U matrix is equal to times F matrix. So, these are reduced equations, and I solve for U, and with that approach I can solve it very easily and fastly, because I have reduced the complexity of my problem by a factor of 4. I am just solving only 1/4 of the problem. So, this is what I wanted to discuss, and what we will do is we will continue this discussion in the next class. I think we have spent a significant time of today on this topic, and with that we close the discussion for today, and we will meet once again tomorrow. Thank you.